Good, happy day whenever you happen to be watching this calculus class. How is everyone doing today? Fantastic. We have a very interesting topic to cover today. We're going to be talking about linear approximations and derivatives of absolute value and piecewise functions. So kind of a big topic today, kind of a big deal. Linear approximations. When that comes to mind, when you think about a linear approximation, like literally what you are thinking about and what's going through your mind is going to be the word approximate. You're going to be taking a line and you're going to be approximating it. Now, this is something that you can do if, like before we had calculators, if you wanted to take the derivative as x gets close to like 3.9, right? Well, what we would say is we'd go with the nearest whole value, say like x goes to 4. That's a lot easier to calculate than 3.9. And we'd call it a linear approximation. So today we're going to be talking about linear approximations. The derivative of the absolute value and piecewise functions is going to come in the next section, not in this section necessarily, but it will come in the next section. So for right now, let's just kind of keep our minds on the linear approximation side of this. So I'll kind of break this up into a couple of things. So first, brightness, needs a little brightness, too shadowy in here. Linear approximation says describe the tangent lines of each function as above or below f of x. So these are below f of x, right? So imagine a tangent line that's going through, say this point right here. Or really any point, right? Let me zoom in, get some zoomage. Say you had a tangent line at this point, so it would look something roughly like this, right? So we have the tangent lines here and here. It's going to look roughly something like this. Well, think about that. If you have a tangent line that is on the underside of something like this here, these tangent lines are below your curve, right? So what I'd like you to write down here is tangent lines are below f of x. Now, on my actual description for the problems here, I'm always going to refer to a curve or a graph as the function name. Never call this thing the graph. Never call it the graph because we don't know what the graph is talking about. But if it says it's f of x like this does here, then I can call this f of x and everybody knows what f of x is. So I never call it the graph, right? I always call it f of x. I never call it the function. I always call it by its name, f of x. All right? It's kind of like if you had a son or a daughter, or if you heard your parents, that's kind of disrespectful, right? You want them to call them by the name that they gave you. So I expect you to do the same for functions. So over here, we've got tangent lines look something like this, and tangent lines look something like this. So here, notice that your tangent lines are above. Wow, I cannot write very neat today, or ever for that matter, are above f of x. Okay, so just a very quick little note about above or below. Really think about this. If you had a tangent line that is below, you're looking at something that's concave up, right? Concave up means it's a U shape facing upwards. It's a happy face if it's concave up. Frowny face if it's concave down, right? So if they are above f of x, then you've got a concave down function. Just kind of a side note there to throw on that. So actually getting into what a linear approximation is. Linear approximations use the tangent line at a f of a as an approximation to the curve y equals f of x when x is near a. What this is saying is that when x is a number like 2.1, then we can use a, call it 2, and say that it's really close to that. That's basically what this is saying. So the equation of a tangent line y minus f of a equals f prime of a x minus a. Well, before you get to down here, if you move this f of a over here, say we add f of a, so it's f of a plus all this other stuff, y is f of x, isn't it? So what we're saying is that if we use an approximate value for a, like if they give us x is, like down here on example 1, you can see it already, 2.97, then I would call a 3, and I'm going to approximate. So that's a linear approximation. This process is called the linear approximation of f at a. Okay? So let's go down to example 1. Now for example 1, it says use linear approximation to find the value of f of 2.97. Linear approximation. Now plugging in 2.97 just as it is, not really a fan. And I do believe that should be, no, that's fine. I'm not really a fan of just plugging in 2.97. Now you could, and it's going to be roughly right, but let's do it this way. First, let's actually multiply this guy out. Remember, I'm trying to find a linear approximation at a certain point. It's kind of like trying to find a derivative at 2.97. All right, a linear approximation is basically the slope right here and then a couple of points thrown in there. So I'm going to need to find this slope, right? I need to find f prime of a. So I'm going to need to take a derivative somewhere. So let's multiply this thing out because right now it's a product rule. If you'll remember, I told you it's always, if you have one term, it's easier to multiply out and use a power rule. So this will be 4x cubed plus x squared. If I just multiply that x squared throughout. And it says use linear approximation to find the value of 2.97. Well, the first thing I'm going to need, I'm going to leave my formula visible up here. The first thing I'm going to need are a couple of items here. Let me write this down. For part A, the first thing I need is a slope. So let's find your derivative here. F prime of x is going to be equal to 3 times 4 is 12x, take one away from the power, plus 2x, your derivative there. And it says I'm trying to find it at 2.97. So what I'm going to do is I'm going to use 3. And I'm going to write that down here. I'm going to choose to use 3. So I'm going to use x equals 3. This is kind of like my a value, right? It's kind of like my a value. So I'm going to choose x equals 3. Remember, this gives you your a. Let me write that down here. This gives you, wow, that's a horrible arrowhead. Let's try that again. Bam! This gives you a. So let's actually find that. If I plug in 3, let's say I want to find the actual point, f of 3, because I'm going to need my point here. F of 3, let's see, we got 3 squared is 9 times 12 plus 6 is 117. F prime of 3, I'm going to need f prime of a, I'm going to need my slope, is 114. Doing the same way. Oh wait, I'm sorry, this is 114. Plugging it up here is 117, I'm sorry. Alright? So to set up my original equation of my tangent line from up here, I've got y minus f of a is equal to f prime of a over x minus a, blah, 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 right? So I've got y minus 117 is 114 x minus 3. Okay? Here's where the linear approximation comes into it. This is the equation of the tangent line at 3. This is the equation of the tangent line at 3. So what I'm going to do here, let's take that 117 over, okay? And I'm going to say that my f of x is approximately 114 x minus 3 plus 117 And what I'm going to do now is plug in f of 2.97. That's 114, 2.97, oops, minus 3, plus 117. And that is going to be roughly 113.58. And 0. Why not? 3 decimal places. Why not? Okay, here's the point of this. If you're going through and you're trying to figure out the value of a function, say at 2.97 or 2.97, you're trying to find f of 2.97. You're trying to actually figure out what will this value be. We did linear approximations a long time ago. This is really kind of like before we had calculators to do this stuff for us. So it is important that you know where this comes from, not necessarily that you use it in the future. I just wanted to show this to you real quick. We don't really use linear approximations very much, especially anymore now that we have all this computing power. But this is what they did in order to guess, do an educated guess as to where the value of a function was at. So I want you to think about this here. It says, for part B, is your approximation high or low? High or low? If you were to graph this thing, I'd come up with something like this. You've got a 0 at negative 1/4, and it's going to go up, 0, and then up like this. And you're trying to find the value at 3. So I want to actually find, or at 2.97 roughly, I want to find at 2.97, really close to 3, what's the value. So what I'm doing is using this linear approximation for my tangent line, and I'm saying that it's kind of hard to plug into this equation, into this big loopy cubic equation, but it's really easy to plug into here. It's easy to calculate off of the line. So it's kind of like what I'm doing is this. I got this curve, right? And what I'm saying is that there's a line that goes like this. You want 2.97. Well, I'm saying that if you plug it into this guy at 3, just beside it, it's going to be really close. It's always easier to plug something into a linear equation than it is a really high-power polynomial. That's what a linear approximation is. It's using a line to approximate what a value is, because it's a lot easier to plug in 2.97 here than it is to cube 2.97. Keep in mind, this is when we were doing it by hand, right? So it's a lot easier to do an approximation with a line than it is to do a cubic function. Okay, on the back. Suppose that the only information we have about a function is f of 4 equals negative 2, and the graph of its derivative is shown. Two things I'd like you to do. Derivative, and from now on, when they tell you it's a derivative or it is f prime, I want you to come over here and I want you to write f prime. And if you want to do it in a couple of 3 different places, I want you to do that. You need to know that this is f prime. This is not f. So I can't just go to 4 and figure out that it's negative. No. That's not how this works. This is f prime. Okay? So it says, suppose that the only information we have about a function is that f of 4 equals negative 2, and the graph of the derivative is shown. Use linear approximation to estimate f of 3.9. Well, let's figure this thing out. 3.9. So what am I going to choose? What number is really close to 3.9? What whole number? So the first thing I want you to write down is I'm going to choose 4. That's my a value. Now they gave us a couple of different things. If I go to f prime of 4, because I need my equation, right? I'm using my equation. Let me write it up here for you so you can see it. F of x